I should point out that for these sorts of problems, what do I want to say here? You will have to do some of these problems, not a ton. It's very much like when we were learning the limit definition of the derivative in 21a, and we had to do that a few times to define some derivatives, and then we moved on, and we learned the power rule, and the product rule, and the quotient rule, and the chain rule, and we probably never use a limit definition after that first exam. Same kind of idea here. You'll probably have to do one of these limit definition of the integrals on the exam. It's fairly standard. You might not, I don't know for sure. And then after that, you'll probably never really use it again in class. Yeah, let's do one more, and then we'll do a few other things. So sure, let's go. Let's make it super fun. Let's estimate. So I will point out that intervals that start at 0 are usually easier. So let's estimate the area. I'm going to make this one. Yeah, I'm going to be smart about this. Let me think for 1 second. I want it to open downwards. Sure. Sorry, I have to think. I kind of want to open it down. Not really, no. I don't care. That's the area under f of x equal to x to the 4th plus, do I want to make this really terrible? No, we're not estimating, we're calculating. X to the 4th plus x squared on the interval from 0 to 2. Okay, so we're doing this, right? It's the limit, n goes to infinity of the sum from k equals 1 to n of f of whatever makes sense times delta x. And again, I'm typically using right endpoints. So I really just kind of want to figure out what's going into this formula here. So let's see. On my interval from 0 to 2, I'm breaking it up into n subintervals. So this is my first subinterval. Typically, we call the right endpoint of a subinterval x sub that subinterval. So like we would call this endpoint x sub 1, this endpoint x sub 2, this x sub 3, where this is like, let me draw my pretend picture here, right? Where this is my first subinterval. This is my second subinterval, and this is my third subinterval. And over here is my kth subinterval. So on the right endpoint of that is x sub k. And the left endpoint of that is x sub k minus 1. That's pretty standard notation. I know that's not actually what's really being done in this class, but it seems worth mentioning because it's what a lot of people do when they teach this. So we can find our delta x, right, our width of our subinterval is going to be 2 minus 0 over n, which is 2 over n. And our x sub k is going to be our delta x times k, which is going to be 2k over n, right? Because our x sub 1 is, well, it's 1, right? It's 1, 2 over n. So x sub 1 is 2 over n, and x sub 2 is 4 over n, and x sub 3 is 6 over n, right? Each of them is 2 over n further. So x sub k is going to be 2k over n, right? We've got k 2 over n lengths, which is 2 times k over n. And then we can rewrite this as, and then we also could write f of x sub k. I wrote k sub k, that should be x sub k. Sorry about that. Is going to be 2k over n to the 4th plus 3 times 2k. Super. All right, so let's throw it all into the formula here. We're going to have the limit as n goes to infinity of the sum of this plus this times this. So that's going to be, and let's multiply this out a little bit. Oh, sorry. Sure. So I'm using right endpoints. That's one of the reasons why. It's not always going to be k times delta x. It's actually always going to be, so let me actually say this. So the right endpoint x sub k is always going to be a plus k times delta x. That is true, right? You're going to start at a, your initial point, which happens to be 0 in this problem. And in the first problem we did when I was doing from -1 to 3, that's why we always got -1 plus k times your delta x, because you're starting at a. So, right, I'm starting at a, so x sub 0 is a plus k times, sorry, a plus 0 times delta x, which is just a. So your starting spot is actually x sub 0. And then x sub 1 is 1 plus 1 times delta x. Well, we exactly went 1 delta x worth over. And then x sub 2 is a plus 2 times delta x. So we're starting at a, and we're moving over 1, 2 delta x's. And then x sub 3 is a plus 3 times delta x. So we're starting at a, and moving 1, 2, 3 delta x's over. So if we start at 1, it would be different. Yes, if we were to start at 1, our x sub k would be 1 plus 2k over n, assuming we were going from 1 to 3. Right, it depends on the interval, exactly. So a is always going to be just like 0. So not exactly. It depends on the interval. Since since the interval is from 0 to 2, in this problem your a is 0. But if the interval was 3 to 5, then your a value would be 3. Exactly. Okay. So let's see. We were plugging in this. So I was going to simplify this. So 2 to the 4th is 16. K to the 4th over n to the 4th plus 2k squared, 2k over n squared is 4k squared over n, times 3 is going to be 12k squared over n, times, k to the 4th, did I make a mistake? I didn't make a mistake so much as I used a formula that I don't actually know. It's fine. Is it fine? It's kind of fine. Let's just change it. Let's do x. I feel like we did x cubed last time. No, we didn't. I'm just making things up. There is a formula for for x to the 4th. For k to the 4th. I don't really want to look it up right now though. So let's just do this one. Let's say it was x to the 3rd plus 3x squared. Sorry about that. This is actually going to be not 16k to the 4th over n to the 4th. It's going to be 8k cubed over n cubed. 12k squared over n, and then we got to multiply by our delta x, which is 2 over n. So multiplying this out, we get the sum from k equals 1 to n. You'll see a lot of people forget to write that sometimes. It's pretty typical. Multiplying this here, you get 16k cubed over n to the 4th plus 24k squared over. Oh, so let me show you how. So I'm about to make a mistake. Actually, I already made a mistake, but it's going to carry through. So 24k squared over n squared. And then I checked the criteria that I mentioned before, is that the power of n should be 1 bigger than the power of k. 4, 3, check. 2, 2, oh, that doesn't check out. I know because the power of n isn't 1 bigger, I have a problem. The problem is I made a mistake back here. Right, when I multiplied this out, I should have had 4k squared over n squared times 3, which should have given me 12k squared over n squared, which means I should actually have an n cubed down there. And now I feel safer about this. But that's always something that should be true. You should have whatever power of k you have, the power of n below it should be 1 larger.
James, I have a quick question. So that, like you said, that's always the case, right? Each time after
that's always the case if you're dealing with polynomial functions.
Okay. Thank you.
You're welcome. And it makes sense, right? Because basically you're always going to have some k over n that's getting raised to a power, so the powers are the same, then you're always multiplying by something that is not k over n. So you're increasing the power of n on the bottom by 1 and leaving the power of k on the top the same. So the power of n should always be 1 larger. So then limit as n goes to infinity. I'm going to break this apart in one step. I'm going to get 16 over n to the fourth times the sum of k cubed plus 24 over n cubed times the sum of k squared. Again, k equals 1 to n, k equals 1 to n. And we're out of space, so let's go to the other side. Oh, it's blank. How nice is that? Awesome. So let's look at that. So limit as n goes to infinity of 16 over n to the fourth times, I'm gonna fill that in a second, and then plus 24 over n cubed times. So what's going to go here is going to be the sum of k squared, which we know is n times n plus 1 times 2n plus 1 over 2, right? This thing here, that's the sum from k equals 1 to n of n squared. Here, what's that? Bringing n times n plus 1 over 2 quantity squared, which is the formula for the sum from k equals 1 to n of k of, oh, sorry, maybe you were going to ask about that. That should be a k squared, and that should be a k. So go ahead with your question, unless your question was, that means.
Oh no, I figured it out, but it wasn't the k squared. Thank you though, James.
All right, so then the same stuff we've been doing before. So again, I don't really want to do any more work with either of these. I want to recognize, so I'll do one thing. I'll write this as, this is the limit as n goes to infinity of, I know that this here is going to be 16n to the fourth plus lower powers of n over 2n to the fourth. And this is going to be 24 times 2 is 48 n cubed. Oh, I did make another mistake. Nobody caught it. Slackers.
James.
Yeah.
For the n, n parentheses n plus 1, is that squared?
Yes, it is squared.
Oh, the whole quantity or just the?
N times n plus 1 over 2. Oh, yeah, the whole quantity. So what should we actually have in the denominator?
4n.
4n to the fourth.
I see. Okay.
And so remember, right, the formula for the sum of k cubed is the formula for the sum of k, which is n plus 1 over 2. This one here is 24 times n times n times 2n, which is 48n cubed, plus lower terms divided by 6. I know I wrote a 2 earlier, but it's actually a 6 divided by 6. End up with, well, the limit of this is just 16 fourths. The limit of this is 48 sixths. 4 plus 8, which is 12. So that's how these problems work. They're kind of a giant calculation pain, but they're doable. You do have to know the formulas for the sum of k or k squared or k cubed, maybe higher powers. But yeah, that's kind of it. So in the last 30 minutes we have, let's do a couple other things. So some people asked me about some various questions. Someone asked me about this one. Someone asked me, if you have the integral from 1 to 14 of f of x dx minus the integral from 1 to 9 of f of x dx, you have the integral from where to where of f of x dx. I think this is a great opportunity to draw a picture. So let's see. Here's what I know. I know that the integral from 1 to 14 of f of x, that's the, that depends. Okay. This area here, right, the area under the curve from 1 to 14 is the blue area plus the red area. Whereas the integral from 1 to 9 is just the blue area. So if you take the blue plus the red and you subtract the blue, what are you left with? You're left with the red area. So that means that the integral from 1 to 14 of f of x dx minus the integral from 1 to 9 of f of x dx is equal to the integral from 9 to 14 of f of x dx. And more generally, here's kind of the rule that's actually being used. The rule is that, and actually I'm going to show you the really kind of the most general version of this rule. These are gross. I long for a day where I don't have to deal with the erases. It's not my problem. So I know it's a small thing, but so here's kind of the general idea. You have some integral from a to b. We can say that the integral from a to b of f of x dx, we can break this integral up as a sum of two integrals, where the breaking point is any point. So I will say it's actually any point, but we'll start by saying it's any point in between a and b. So you can pick some point like, say, c, and say that, okay, well, the area under the curve is this area, which is the integral from a to c of f of x dx, plus this area here, which is the integral from c to b of x dx. And again, we can use colors if you want, right? You can say that this is the red part. This is the blue part. Okay, now here's what I think is actually kind of the neat thing. C doesn't have to be between A and B. It also totally works if your picture is like this. Just like, huh? So what we're saying now is that this area, let's call this the area in black. This area in black, maybe black's the wrong choice, is equal to the area in red and I'm not going to color the area in blue because it's actually kind of a problem. Right? The integral from C to B, well, when you go from right to left, that gives you like a negative. So what I would really rather do is I would really rather write this as the integral from A to B, sorry, A to C of f of x dx. And then I'm going to change the order, but then I have to give myself a minus sign, exactly. Minus the integral from B to C of f of x dx. Oh, but the integral from B to C actually is this part over here. So the red area minus this, make it green, right? The red area minus the green area totally is the black area there. So it actually does work. So what's kind of cool is that as long as the function is defined everywhere, you can take an integral from A to B and break it up anywhere. So that you do the integral from A to something and the integral from something to B. So just for the fun of it, we could say, well, I know that the integral from, say, like, what was I going to do? Yeah. So, well, yeah, this is kind of silly, but let's say I wanted to find the integral from 2 to 10 of x squared. I could totally break it up at 0. There's a Homer problem kind of related, but not super related. It's kind of there. I don't know what the number is, but somebody definitely asked me this one. There is a Homer problem like it, but I don't have the numbers. So yeah, but you can totally break this up at 0. You can say it's integral from 2 to 0 plus the integral from 0 to 10. Would I do this? No. But could I do this? Yes. And then you could say, oh, this is the negative integral from 0 to 2 of x squared dx plus the integral from 0 to 10 of x squared dx. It's kind of neat. Sometimes, so the reason I mentioned this is because sometimes people do talk about finding the area under x squared always starting at 0. So we know that this particularly is 2 cubed over 3, and this particular is 10 cubed over 3. Because when you integrate x squared to x cubed over 3. So yeah, you can. The caveat is the function has to be defined on the entire interval that you're working with. So if you're going to break it up somewhere way out in yonder, you can't be undefined anywhere between there. So like, for example, if I was doing the integral from from like 1 to 25 of 1 over x dx, I could not break it up. I'd say like a negative number. Because 1 over x is undefined at 0, and 1 to negative 2 encompasses that 0 value, and that's a problem. That's what's called an improper integral, which we will deal with later, but not yet. It is nice, yeah. Let's see, we had a couple other things. Yeah, we got time. We got time. So typically, we're going to be talking about finding the area under a lot of different curves, which are going to be definite integrals. And usually the rule of thumb is you want to do the least amount of work possible. Sometimes that means seeing a trick. Sometimes that means recognizing that that thing is just a geometric shape that I know how to find the area of. For example, I want to find the integral from -4 to 4 of, I'll start easy, the square root of 16 minus x squared. Can we integrate this? Can we anti-differentiate this? Not yet. Will we be able to eventually? Yes, we totally can, but not yet. We need trig substitution. But I want to find the area under this curve. Well, I know how to. So again, I should reemphasize. This expression means we want to find the area under y equals to the square root of 16 minus x squared between -4 and 4. Okay, we can graph this. Do we know what the graph of this is? Let's see, if I plug in 4 for x, I get 0. If I plug in -4 for x, I also get 0. If I plug in 0 for x, I get 4 for y. I gotta hit these 3 points. It's not a parabola.
It's a semicircle.
Semicircle. And it might be easier to see if you square both sides of this. Say y squared is 16 minus x squared, and then add x squared over, and you get x squared plus y squared equal to 16. This is the equation of the full circle, but since y is equal to the square root, we know y has to be positive. So we get the semicircle, and hey, I know the formula for the area of a circle. So do you. But this is half a circle, so it's going to be 1/2 pi times the radius squared. And that's it. That's going to be 8 pi. So if you recognize something as a circle or a semicircle, you can use your knowledge of the area of a circle. In a similar way, if I was asked to find, say, the integral from -4 to 0 of the square root of 16 minus x squared, I would be like, oh, well, now I'm only finding this area, which is a quarter of a circle. So it's going to be 1/4 the area of the circle, which is just going to be 4 pi. So definitely use the geometric formulas we know to kind of separate things. Not separate, to find areas of known shapes rather than trying to. Anti-differentiating this is actually not easy. It can be quite challenging. Some teachers do crazy things. Really, there's one teacher, he's not your teacher, who likes to make students find the area from like say 0 to 2 of this shape. So like find this area. And for that, you actually can't just use a fraction of a circle because it's not just a fraction of a circle. But what you can do is some weird, like, you can be like, well, I can find like the area of this part using a sector because I can find this angle, and then the area of this part is like a triangle. It's super complicated and we don't need to bother with it. But yeah, you can totally do that. It does work, but we'll use calculus to do it.
James,
Yeah.
I have a question. So for that one problem we just did, because we only have half a circle and we know that we like the area of a circle is just pi r squared. Oh, okay.
Yep.
Okay, then that.
That's why this is 1/2 of the area of the circle.
Okay, that makes sense.
And for this one, I did 1/4 of the area of the circle. So circles come up, or semicircles come up quite often. The other thing that comes up are triangles. Often in the context of an absolute value. So let's say I want to find, I don't know, this is going to be similar, but not quite the same as the problem someone gave me. I want to find the integral from 0 to 6 of, it's kind of ugly, but fine, 8x minus, the opposite of 8x minus 7. You could, and in fact, I will show you after we do it the easy way, you could break this up into a couple integrals and do it the hard way. But here's the easy way. Draw the thing. Let's see, and I'm going to plug in the endpoint. So when x is 0, 0 minus 7 is -7, but the opposite value is 7. So in that sense, there it's 7. And then I plug in 6, 48 minus 7 is 39. So over here, when I plug in 6, I get a y value of 39. And then I'm going to have my usual absolute value shape. It's going to do something like that. I need to know this point here. I need to know what value makes this equation, this function equal to 0. So I'm just going to set 8x minus 7 equal to 0, and I'm going to get x equal to 7/8. So right there, that's 7/8. Well, look, I've got a couple triangles. We can find their areas. Let's say this is A1, let's say this is A2. So the first triangle, the area is 1/2 the base, which is 7/8, times the height, which is 7. And that's going to be 49/16. For the second triangle, the area is again 1/2 the base, which is, I'm just going to write 6 minus 7/8, times the height, which is 39. All right, that's kind of terrible, but fine. 6 is 48/8. 48 minus 7 is, I feel like I'm making a mistake here. 1 second. I just want to make sure I'm not doing something stupid. I plugged in 6. I did do something stupid. Not stupid, but just I made a mistake. And when I plugged in 6 here, I got 48 minus 7, which should be 41, not 39. Usually you get the same number like squared. That's why I was kind of like, oh, I feel like I should be getting 41 times 41 when I do this. And I do. I get 1/2 times 48 eighths minus 7 eighths is 41 eighths times 41. So I get 41 squared over 16. And I add them together. So my answer is that the area is 49/16 plus 41 squared, which is 1,600, and no, it's, yeah, it is, it's 1,681 over 16. So you end up with 1,730 over 16. Or you could do this the terrible way, right? This is still actually not the easiest, right? The numbers are a little janky, but if you really wanted to, you could say, okay, well, let me just write it this way. From here to here, this line is y equal to 8x minus 7. From here to here, though, this line is y equal to negative 8x minus 7. So if you wanted to instead, you can say, okay, well, I'm going to say, let me draw the picture again. This is y equals negative 8x minus 7. This is 7/8. This is 6,1. 0,7. This is y equal to 8x minus 7. Another way you can calculate the area is by doing, well, this area is going to be the integral from 0 to 7/8 of this function, which is negative 8x minus 7. And then this area is going to be the integral from 7/8 to 6 of this function, which is 8x minus 7. Well, that seems terrible. Yeah. So then we would just do the thing, right? You would get negative 8x squared over 2 plus 7x from 0 to 7/8 plus 8x squared over 2 minus 7x from 7/8 to 6. You don't want to do this. You want to do it the other way. So do it the other way. Oof.
Wait, James, I have a quick question. So we got did we get our 8 sorry, so 8x minus 7 we took the antiderivative?
Right, and got 8x squared over 2 minus.
Okay, I remember now. Yeah, thank you, James.
Problem. Let's see what else.
James, I have a quick question. Sorry.
Yeah.
So how did you get the negative parentheses 8x minus 7?
Sure. So here's the thing about absolute values. The absolute value of anything is equal to a piecewise function. Mm-hmm. It's just what you've already got if what you've already got is positive. Right, so what's the absolute value of like 8 times 2 minus 7? Well, the absolute value of 16 minus 7 is the absolute value of 9, which is just 9. So if your stuff is already positive, then the absolute value of your stuff is just what you've already got, because you don't need to do anything to it.
Yes.
But if your stuff happens to be negative, then to take the absolute value of that stuff, you need to change a negative into a positive. And the way you change a negative number into the same positive number is by multiplying it by -1. That's how I'm getting. So this part over here, right? If you plug in, say, like x equal to 0, you get 8 times 0 minus 7, which is -7. So to change that, if I plug in 0, 0 minus 7 is -7. To change that to +7, I have to multiply the whole thing by -1 to get +7.
Oh, so you're pretty much just getting rid of the -7, like the negative symbol.
Well, no, I'm really saying that this whole portion of the absolute value graph is the line y equal to negative 8x minus 7.
Oh, okay.
And this whole line is the line y equal to 8x minus 7.
Okay.
And that's always how piecewise functions work. One part of it is y equal to some line, and the other part of it is y equal to the negative of that line.
Yeah, like the opposite, pretty much.
Exactly.
Okay, for sure. Yeah, I get it now, for sure. Thank you so much, James.
Welcome. And then notice, right, this condition here, if you solve for x, is exactly that x is bigger than 7/8, which is exactly this part here. And this condition is exactly that x is less than 7/8, which is everything on that side there. But again, shouldn't do it this way, right? You should just be like, hey, I've got triangles, and we know how to find the area of triangles.
Quick thing, I saw another way of approaching this problem from online, and it's integration by parts.
For an absolute.
For absolute value, and I was wondering.
I would never use integration by parts, because you only really need to use integration by parts if you have like two different types of functions multiplied together. Can you tell me what work was done exactly?
Actually, I think it'll be better put this on discussion board instead, because it's a bit long.
Yeah, I'm just because integration by parts is when you're doing like the integral of v du equal integral of u dv equals uv minus the integral of v d.
Yeah.
And I've never seen this type of integral done that way. Not that it couldn't be, I'm just not familiar with that particular type of thing. But yeah, I'm happy to, if you put it on discussion, happy to take a deeper look at it and see what's going on. So again, the general statement I will make is, even if it's possible to do it using integration by parts, we're all best off by drawing this and
Yeah, for sure.
using triangles. Now, if your function is more complicated in here, right, if it's like the absolute value of like 8x squared minus 7, then you're out of luck because you don't get just triangles, but that's another story. Let's see. What else do I have? How much time do I have? That's the end of this assignment. Trying to see if there's anything else in this assignment that we didn't really cover. No, I think one thing. So, okay, I got 4 minutes left. I'll say one more thing. This might not be super important, but some people do spend some time focusing on it. So some people, yourselves included, might wonder, well, how do we know that, for example, the sum from k equals 1 to n of k squared, how do we really know that that's n times n plus 1 times 2n plus 1 over 6? Right, I showed you guys the other one for sum of k equals 1 to n of k. Like, oh yeah, totally equals n times n plus 1 over 2. How do we know this one? Well, there is a way to do it. It's a little bit tricky, but someone might show it to you and maybe expect you. I definitely remember when I took 21B many years ago, we actually did talk about this in class, and there was like a test question on it. So here's how you do something like this. You deal with a telescoping sum of the following. K plus 1, use the next highest power, cubed minus k cubed. And we're going to calculate this in two different ways. First, I'm just going to write it out. When I start writing this out, so I start at k equals 1, I get 2 cubed minus 1 cubed. Plus, then k equals 2, I get 3 cubed minus 2 cubed. And then for k equal to 3, I get 4 cubed minus 3 cubed. And then I get a bunch of terms. And then the last couple terms are when k equals n minus 1, I get n minus 1 plus 1, so n cubed minus n minus 1 cubed. And when k equals n, I get n plus 1 cubed minus n cubed. Now, the thing about this, the reason it's called a telescoping sum is because essentially all the terms cancel except for the first and the last term. So this 2 cubed and this negative 2 cubed cancel. This 3 cubed and this negative 3 cubed cancel. This 4 cubed and the negative 4 cubed that would be in the next term cancel. All the way to the one before this, right? So like you would have n minus 1 cubed minus n minus 2 cubed. So that would cancel with that. And then the n cubed cancels with the minus n cubed there. And you're left with the fact that this is equal to negative 1 cubed plus n plus 1 cubed. Which if you multiply this out, it's equal to n cubed plus 3n squared plus 3n plus 1 minus 1. And if you factor out an n, you get n times n squared plus 3n plus 1. Sorry, plus 3. Yeah, I don't want to do that. So that's one way of calculating this. The n cubed plus 3n squared plus 3n. Great. I'm going to calculate it a different way. I'm going to break it apart. We're almost out of time. You guys are obviously welcome to leave if you need to. I'm going to finish this because I started it. I did, let me make sure. I believe I caught a screenshot of everybody, but let me double make sure I got one just so that I can take the attendance later. All right, so the other way we're going to do this is I'm going to break it up as the sum k equals 1 to n of k plus 1 cubed minus the sum. Oh, no, I'm sorry, that's not exactly what I'm going to do. I'm going to multiply it out. So I'm going to have the sum of, so k plus 1 cubed minus k cubed. I'm going to multiply that out as a sum from k equals 1 to n. K cubed plus 3k squared plus 3k plus 1 minus k cubed. These cancel. And I'm going to use the other formulas we know. Right, I'm going to break this up as 3 times the sum of k squared plus 3 times the sum of k plus the sum of 1. Right, because this is 3k squared, 3k, 1. And now we're going to use the formulas for those. You're welcome, Julia. And everybody else is thank you. I'm sorry. So this is 3 times, the formula for this is, oh no, we're trying to solve for that one, sorry. We don't know that one. This is equal to 3 times the thing we're trying to solve for. Plus, we know the formula for this is 3 times n plus 1 over 2, plus the formula for this is n. And we know that this is equal to that. N cubed plus 3n squared plus 3n. Right? Right. So then what we can do is we basically bring this over. Let's multiply everything by 2. So I've got 6 times the sum from k equals 1 to n of k squared. Multiply by 2 to get rid of this. So I've got plus 3 times n squared plus n plus n, sorry, plus 2n, right? Multiplying everything by 2 equals 2n cubed plus 6n squared plus 6n. Subtract the 3n squared, so you're going to get, let's see, 2n cubed, 6n squared minus 3n squared is 3n squared, and then 2n plus 3n is 5n, so 6n minus 5n is n. And then this totally factors as 2n, is n times 2, geez, come on, James. I mean, there is a 2, but times n plus 1 times 2n plus 1. And then we divide by the 6. And we exactly get that the sum of k squared is n times n plus 1 times 2n plus 1 over 6. So that's how you would show something like that is what it's actually equal to. I don't imagine you'll be asked to do this, but someone might talk about how you actually find these formulas. And